Sean Carroll, The Particle at the End of the Universe, How the Hunt for the Higgs Boson Leads Us to the Edge of a New World. Welcome to the world of the Higgs boson, the elusive particle that has captivated scientists and the public alike. In The Particle at the End of the Universe, Sean Carroll takes us on a journey through the complex and fascinating landscape of modern science. The book starts with a primer on atoms and their constituent particles, protons, neutrons, and electrons, then leads us into the discovery of smaller subatomic particles like the leptons and quarks. Along the way, we'll delve into the four fundamental forces of nature: gravity, electromagnetism, strong and weak nuclear forces that govern the behavior of particles, and finally explore the elusive Higgs field, responsible for the mass of particles. This introduction will provide you with a snapshot of the world of particle physics and the hunt for the Higgs boson.
The tiny world of atoms. Atoms are the building blocks of everything, and they are made up of even smaller particles called protons, neutrons, and electrons. Every atom has a unique atomic number that identifies it on the periodic table. Electrons orbit the nucleus of an atom, and atoms can combine to form molecules. Despite their small size, there's an even stranger world within atoms that scientists have discovered. The bounty of subatomic particles. Scientists have discovered a vast array of subatomic particles, including leptons and quarks, through studying neutron decay in cosmic rays. These particles include different types of neutrinos and leptons such as muons and taus, as well as 6 different kinds of quarks which serve as building blocks for protons and neutrons. The 4 fundamental forces. Have you ever wondered why you don't soar off towards the horizon if you jump out of a window? This is because of gravity, which is one of the 4 fundamental forces in the universe. The other 3 are electromagnetic force, strong nuclear force, and weak nuclear force. Electromagnetic force is responsible for the structure of the atom, while strong nuclear force ensures stability within it, and weak nuclear force is responsible for radioactive decay and nuclear fusion. These forces are critical for not just understanding our universe but also for our very existence. The importance of mass and the Higgs field. Have you ever wondered why some things are heavier than others? The answer lies within the concept of mass. Mass can be thought of as the resistance you feel when trying to push an object. This concept can explain why a car is harder to push uphill than a bicycle. Mass is derived from the interactions of particles within the Higgs field. Protons have more mass than electrons because they have a stronger interaction with the Higgs field. The Higgs field is essential for mass to exist in our universe, as all particles would have zero mass without it, making life impossible. The Higgs boson is the boson related to the Higgs field, and it is everywhere since the Higgs field permeates the entire universe. The bosons that make up the fundamental forces of gravity, electromagnetism, strong, and weak nuclear forces are also present in countless combinations and play a crucial role in the composition of our universe. In conclusion, understanding the importance of mass and the Higgs field helps us comprehend the fundamental nature of our universe. Simplifying particle physics. Particle physics can be a complex subject, but understanding the concept of the Higgs field through analogies can simplify it. The Higgs field causes particles to have mass, and it can be compared to a crowded party or swimming in water. These analogies help in understanding the concept and prepare for the search for the Higgs boson. Inside the particle accelerator. The Large Hadron Collider is a circular particle accelerator that smashes particles at high speeds to uncover the universe's secrets. Through this experiment, scientists can understand how the universe was created. The LHC is shaped like a ring and powered by electric currents that are cooled by liquid helium to avoid overheating. Despite the danger, scientists believe the benefits of this experiment outweigh any potential risks. The search for the elusive Higgs boson. When particles collide, scientists hope to catch a glimpse of the Higgs boson. Despite its short lifespan, scientists designed 2 experiments, CMS and ATLAS, to detect its presence. The experiments incorporated different detection mechanisms and specialized layers to narrow down specific particles. The inner detector records particle paths, while two calorimeters measure energy in the muon detector, catches muons. The hope is that the detection of particles, thrown off as the Higgs boson decays, may provide evidence of its elusive presence. The discovery of Higgs boson. After years of experimentation at the Large Hadron Collider, scientists used the falsification process to verify the discovery of the Higgs boson. By disproving their initial hypothesis, they were able to sift through the statistical data and declare the existence of the particle. This discovery, which took more than 50 years to achieve, raises a more complex question: what can we do with it? The Higgs boson, more than just a particle. The discovery of the Higgs boson allows scientists to better understand the universe's mysteries, detect dark matter, and possibly develop new technologies. Scientists may wonder what the significance of discovering the Higgs boson was. The answer to that is quite simple: studying the Higgs boson can lead to a better understanding of the universe's mysteries. It helps to explain the different parts of what physicists call the Standard Model, which helps understand the interactions in both ordinary matter and bosons. However, when scientists measure the total amount of matter and ordinary matter in the universe, they find that these numbers differ, suggesting an existence of dark matter. The Higgs boson can potentially help us detect dark matter by measuring whether matter is generated as the particle decays. Furthermore, the discovery of the Higgs boson could lead to the development of new technology. Learning from history, there were unexpected relevant applications of Einstein's theory of relativity. This theory is beneficial for GPS technology. While not immediately obvious, his theory helped to communicate with satellites in orbit and determine one's position on the ground. The Higgs boson may also lead to new discoveries with various possibilities to uncover.
As we reach the end of our journey through the fascinating world of particle physics, we've learned about the fundamental building blocks of matter, the four forces that govern the universe, and the elusive Higgs particle. The discovery of the Higgs boson at the Large Hadron Collider, LHC, in 2012 marked a significant milestone in our understanding of the universe. By piecing together evidence from the LHC and observing how particles interact with the Higgs field, we can better understand the mysteries that still remain, such as dark matter and the potential applications of this newfound knowledge. The world of particle physics is a complex and ever-evolving field, and with each new discovery, we move one step closer to understanding the hidden tapestry of the universe.